Assembly language programming, learning objectives. In this chapter, the user would learn the following in detail. Machine and assembly language. Turbo assembler, Tasm. Assembly language of Intel 8086. Simple examples based on arithmetic and character operation. Introduction. Program is a set of codes or instructions. Programming language is machine understandable language. Types of programming languages are low-level language or machine-level language, assembly language or middle-level language, high-level language. Machine language, program written using only zeros and ones. Machine languages are the only languages understood by computers. Machine language codes are in the form of numbers. Strings of numbers giving machine-specific instructions. Example, +1 3000 42774, +1 400 593 419, +1 200 274027. Drawback: machine languages are almost impossible for humans to use because they consist entirely of numbers. Assembly language, program written using mnemonic codes or assemble codes. An assembly language contains the same instructions as a machine language, but the instructions and variables have names instead of being just numbers. High-level language, program written using English-like statements. Very simple to read and understandable by human beings. Codes similar to everyday English. Uses mathematical notations translated via compilers. Terminology. Machine language, fundamental instructions expressed as zeros and ones. Assembly language, human-readable equivalent of machine language. Assembler converts assembly language program to machine language. Compiler converts high-level language program to machine language. Stored program. Program can be stored on computer with its data and be manipulated as if it were data. Machine and assembly language. Machine code instructions. Instructions are patterns of bits with different patterns corresponding to different commands to the machine. Machine code or machine language is a system of instructions and data directly executed by a computer's central processing unit. Example, 2 Motorola MC6 8000 instructions. Assembly languages. A much more readable rendition of machine language called assembly language uses mnemonic codes to refer to machine code instructions rather than simply using the instructions' numeric values. For example, on the Zilog Z80 processor, the machine code 00000101, which causes the CPU to decrement the B processor register, would be represented in assembly language as DEC-B. The following are common types of instructions. Moves. Set a register to a fixed constant value. Move data from a memory location to a register, a load, or move data from a register to a memory location, a store. All data must be fetched from memory before a computation may be performed. Similarly, results must be stored in memory after results have been calculated. Read and write data from hardware devices and peripherals. Computation. Add, subtract, multiply, or divide. Typically, the values of two registers are used as parameters and results are placed in a register. Perform bitwise operations taking the conjunction or disjunction and or of corresponding bits in a pair of registers or the negation not of each bit in a register. Compare two values in registers, greater than, lesser than, greater than or equal to, or lesser than or equal to. Control flow. Jump to another location in the program and execute instructions there. Jump or branch to another location if a certain condition holds. Jump to another location but save the location of the next instruction as a point to return to. Assembly code overview. Opcodes. Opcodes are operation codes, the codes assigned to each processor instruction. Operands. Operands are the objects used by the operation represented by the opcode. Mnemonics are the human-readable names given to individual opcodes. Processor instructions are often classified into groups such as data transfer instructions, example mauve, mauve-x, push, pop, xch. Arithmetic instructions, example inc, add c, dec, sub b, mul, div. Logic instructions, example clear, set b, anl, rrc, orl, xrl. Control transfer, example AJMP, LJMP, JMP, ACALL, LCALL, RET, DJNZ, JNB, a call. Assembly programming overview. Explanation. An assembly program is written using a simple text editor. Each assembler has specific syntax rules. The structure of the source file and the names that are used to represent assembler directives, opcodes, and operands. There are also syntax rules regarding comments in the file. Assembler directives are used by the assembler to control assembler operation. For example, the assembler can be directed to output program code at a specific address using the .org or .org directive. Assembly language syntax. Syntax. Each line of a program is one of the following: an instruction, an assembler directive or pseudo-op, a command. White space between symbols and case are ignored. Comments beginning with semicolon are also ignored. Label. Mnemonic operand 1, operand 2, semicolon, comment. Label. The first field, which is optional, is the label field, used to specify symbolic labels. A label is an identifier that is assigned to the address of the first byte of the instruction in which it appears. Presence of a label is optional. Syntax. Mnemonic. The second field is mnemonic, which is compulsory. All instructions must contain a mnemonic. Operand. The third and following fields are operands. The presence of the operands depends on the instruction. Some instructions have no operands, some have one, and some have two. If there are two operands, they are separated by a comma. Comment. The last field is a comment field. It begins with a delimiter such as the semicolon and continues to the end of the line. Example, a typical assembly language instruction. Developing and executing assembly language programs. Steps involved in developing and executing assembly language programs. Write an assembly language program using ordinary text editors such as WordStar, Editor, and so on. The assembly language program text is an input to the assembler. Then, the assembler translates assembly language statements to their binary equivalents, usually known as object code. During assembling process, assembler checks syntax errors and displays them before giving object code module. The object code module contains the information about where the program or module is to be loaded in memory. Steps involved in developing and executing assembly language programs. If the object code module is to be linked with other separately assembled modules, then it contains additional linkage information. At line time, separately assembled modules are combined into one single load module by the linker. The linker also adds any required initialization or finalization code to allow the operating system to start the program running. Assembler directive. There are some instructions in the assembly language program which are not a part of the processor instruction set. These instructions are instructions to the assembler, linker, and loader. These are referred to as pseudo operations or as assembler directives. The assembler directives enable the user to control the way in which a program assembles and lists. They act during the assembly of a program and do not generate any executable machine code. The assembly language requires assembler directives for performing the following basic functions: to indicate starting location of the memory where the data block is stored and starting location of the memory where code is stored. To define different types of variables or to set aside one or more storage locations of corresponding data type in memory. To indicate the assembler about the values of the variables. To indicate start and end of subroutine program. Commonly used assembler directives. Origin. This assembler directive tells assembler that where to place the data block in the memory or where to start loading of object program in the memory. DB, DW, DD, DQ, and DT. These directives are used to define different types of variables or to set aside one or more storage locations of corresponding data type in memory. These are known as data control directives. DUP. The DUP directive can be used to initialize several locations and to assign values to these locations. EQU. The EQU directive is used to redefine a data name of variable with another data name variable or immediate value. The directive should be defined in a program before it is referenced. The procedures in the programs can be defined by proc directive. The procedure name must be present, must be unique, and must follow naming conventions for the language. After the proc directive, the term near or far are used to specify the type of the procedure. NP. NP directive is used along with the proc directive. NP defines the end of the procedure. Commonly used assembler directives. Number notation. Most of the programming languages allow specifying the variables' values or numbers in various types of number systems such as binary, decimal, hexadecimal, etc. To tell the assembler that the number is specified using particular number system, assembly language provides number notation for each number system that it supports. Example. In each example, the sign hash in front of the value of an operand is used to indicate that this value is an immediate operand. Turbo assembler, Tasm. Explanation. The turbo assembler, mainly PC-targeted assembler package. Tasm worked well with Borland's high-level language compilers for the PC such as Turbo C and Turbo Pascal. Steps to work on Tasm. C:\tasm, edit filename.asm. Save file with filename.asm. C:\tasm, tasm filename.asm. C:\tasm, t-link filename plus io. C:\tasm, td filename. Macros in Turbo Assembler. Macros are substituted when the program is compiled to the code which they contain. Syntax. Macros make a program bigger if a user overuses it. Use local directive to avoid label and variable confusion. Macros in Turbo Assembler. Usage. Example. Prints out a message to the screen. Macros can also have parameters. Number of parameters only restricted by line length. Example. Add first and second parameters and put result in third parameter. Add macro num1, num2, result. Assembly language Intel 8086. The Intel 8086 family. First started in 1981 with the 8086. The latest edition was the Pentium released 13 years later in 1994. backward compatible with each other. Each new generation chip has added features and more speed than the previous chip. Very few computers in use that have the 8088 and 8086 chips in them. They are very outdated and slow. We depend registers, locations in the CPU where a number can be stored and manipulated. There are three sizes of registers, which are 8-bit, 16-bit, and on 386 and above 32-bit. There are four types of registers: general purpose registers, segment registers, index registers, and stack registers. Registers, main registers, and stack registers. The main registers are 16-bit registers. There are four general-purpose registers: AX, BX, CX, and DX. They are split up into 8-bit registers. AX is split up into AH, which contains the high byte, and AL, which contains the low byte. On 386 and above, there are also 32-bit registers. These have the same names as the 16-bit registers but with an E in front, that is EAX. User can use AL, AH, AX, and EAX separately and treat them as separate registers for some tasks. Index registers. These registers are sometimes called pointer registers. They are 16-bit registers and are mainly used for string instructions. There are three index registers: SI, source index, DI, destination index, and IP, instruction pointer. On 386 and above, there are also 32-bit index registers EDI and ESI. User can also use BX to index strings. Stack registers. BP and SP are stack registers and are used when dealing with the stack. The designers of the 8088 decided that the maximum need for memory space will be 1 megabyte. So, the chip they built cannot go above that. The problem is, to access a whole megabyte, 20 bits are needed. But registers only have 16 bits, so 4 more bits are needed. Segments and offsets. Another way to do the addressing with 2 registers but not using 32 bits. Computes every single address. The segment address as well as the offset are needed. A segment is 64,000 bytes long. To address a location inside a segment, the offset should be 16 bytes long. The stack. The number of registers used is low. Since data is huge, how do they manage to manipulate the data? There is something called a stack, an area of memory to which one can save and restore values to. To physically imagine this, one can consider a stack of plates. The last one that is kept on top is the first one that a person takes off. This is sometimes referred to as last on, first off, LOFO, or last in, first out, LIFO. Do not put too much data in the stack. Memory models. There are several memory models available. In standalone assembly language programming, the small is usually the best choice. In the table, those models are described. Equates. In assembly language, constant values are known as equates, referring to the EQU directive that associates values with identifiers such as base address and max value. It is important to note that equates may appear anywhere in the program without restriction. Several examples are given. Count EQU 10. Number EQU 5. Price equals count into number. My cat EQU, Gilly. After declaring a symbol with EQU, a user cannot change its associated value. The values declared with equal to sign can be changed. EQU can declare all kinds of equates, including numbers, expressions, and characters. Numbers in binary. How numbers are represented in computers. Numbers are stored in binary base 2. There are several terms which are used to describe different size numbers. Numbers in binary. The nibble is 4 bits or half a byte. It has a maximum value of 15. 1111 equals 15. This is the basis for the hexadecimal base 16 number system, which is used as it is far easier to understand. Hexadecimal numbers that begin with a letter are prefixed with a 0. 1 byte colon 00000000 equivalent with 2 nibbles or 8 bits. A byte is 8 bits or 2 nibbles. A byte has a maximum value of FFH 255 decimal. Numbers in binary. A word is a 2-byte data. The maximum value that can be represented using a word is 65535. It is obvious that if a bigger number has to be represented, the necessary number of bytes will increase. Above, MSD means most significant digit and LSD means least significant digit. A word will be represented as shown. In memory, bytes are stored one after another. Each one has an associated address. Often, data needs more than 1 byte, every number greater than 256. Now, use a word to represent this number. The most significant byte is stored at higher address than LSB. Binary arithmetic and logic. Programming in assembly language does not require a lot of binary computation from programmer. However, there are several operations that have to be done by a programmer. These operations are count from 0 to 16 in binary, convert values into binary, hexadecimal, and decimal, logical operations and, OR, and XOR, differences between logical representations of positive and negative numbers in binary. The table shows the counting from 0 to 16. Convert values into binary and hexadecimal. In exchange, it is important to know how many bits one needs to represent a number. Use the following table. A user can tell right away using the table how many bits are needed to represent a specific number. Logical operations AND, OR, and XOR. As in mathematics, to perform operations, a user needs at least 2 operands. Denote them as A and B. For AND, the truth table is as follows. Basically, the result is 1 only if both operands are 1. For OR, the truth table is as follows. Basically, the result is 1 only if at least one operand is 1. For XOR, the truth table is as follows. Basically, the result is 1 only if the operands have different values. The Mauve instruction. The instruction used to move an operand from one location to another one is Mauve. It can be used to address general purpose register or The Mauve instruction. Several examples of using this instruction are Mauve AX, 15, put 15 into AX. Mauve BX, 25, put 25 into BX. Mauve CX, 35, put 35 into CX. Mauve DX, 45, put 45 into DX. Mauve AX, BX, put the content of BX into AX. Mauve BX, CX, put the content of CX into BX. Mauve CX, DX, put the content of DX into CX. The push and pop instructions. These instructions are used to work with the stack. Push will put a data in stack. Pop will take the data from stack. The syntax is push data and pop register. Types of operands. There are three types of operands in assembler: immediate, register, memory. Immediate, number which will be known at compilation and will always be the same, for example 20 or A. Register operand, any general purpose or index register, for example AX or SI. Memory operand, a variable which is stored in memory. The INT instruction. The INT instruction calls a DOS or BIOS function, which are subroutines to do things that a user would not write a function, for example change video mode, open a file, etc. The syntax is INT space interrupt number. Some examples are INT space 21H calls DOS service. INT space 10H calls the video BIOS interrupt. Most interrupts have more than one function. This means that a user has to pass a number to the function he wants. This is put in AH. The INT instruction. To print a message on the screen, mauve space AH, 9. Subroutine number 9. INT space 21H, call the interrupt. First one has to specify what to print. This function needs ds:\dx to be a far pointer to where the string is. The string has to be terminated with a $sign. This would be easy if ds can be manipulated directly. To get round this, one has to use AX. Declaring a string. To declare a string, a user has to type message db space hello world $. Notice that the string is terminated with a $sign. db is short for declare byte, and the message is an array of bytes. An ASCII character takes up 1 byte. Data can be declared in a number of sizes: bytes db and words dw. Ideal, model, small, stack 266. Insert include, file name directives here. Insert EQU and equals equates here. Data seg. If an appropriate error occurs, the program should halt, store an appropriate error code in Xcode, and execute a JMP exit instruction. To do this from a submodule, declare the exit label in an extrn directive. Add. The add instruction will add together two operands. The results are stored in the first one. Add reg, reg. Add reg, mem. Add mem, reg. Add mem, con. Example: add space AX, 10. The AX is less than -AX plus 10. Sub. The sub instruction will subtract one integer from another. The results are stored in the first one. Sub reg, reg. subreg, mem, submem, reg, submem, con. Example, sub AH, AL. The AH is lesser than minus AH minus AL. Inc, dec. The inc instruction will increment its operand by 1. The dec instruction will decrement its operand by 1. Inc reg, dec reg, inc mem, dec mem. Dec AH, the AH is lesser than minus AH minus 1. IMUL. The IMUL instruction can use 2 or 3 operands. The first form multiplies 2 operands together and stores the result in the first operand. IMUL reg 32, reg 32. IMUL reg 32, mem. IMUL reg 32, reg 32, con. IMUL reg 32, mem, con. Examples, IMUL AX, var. The AH is lesser than minus AH into var. IDIV. The IDIV instruction divides the contents of AX by the instruction operand. If the operand is a word value, then the content of dx AX is divided by the operand. The first form multiplies 2 operands together and stores the result in the first operand. IDIV reg 32, IDIV mem. Example, IDIV BX. The AX is lesser than minus AX divided by BX. Divides the component of AX by the content of BX. AND, OR and XOR. AND, OR and XOR are specific for logical operations. AND reg, reg. AND reg, mem. AND mem, reg. AND reg, con. OR reg, reg. OR reg, mem. OR mem, reg. OR reg, con. XOR reg, reg. XOR reg, mem. XOR mem, reg. XOR reg, con. Example, AND AX, 01H will clear all but the LSB of AX. SHL, SHR. These instructions shift their first operand to the left or to the right padding the resulting positions with 0. The shifting order is given by the second operand. SHL reg, con. SHL mem, con. SHR reg, con. SHR mem, con. OR reg, reg. OR reg, mem. OR mem, reg. OR reg, con. Example, SHL AX, 1. Multiply the AX by 2 if MSB is 0. SHR AX, CL. Store in AX the result of dividing the content of AX by the content of CL. Character output. The task here is to display a single character on the screen. There are 3 elements involved in carrying out this operation using the INT instruction. User specifies the character to be displayed. This is done by storing the character's ASCII code in a specific 8086 register. In this case, a user can use the DL register, that is, a user uses DL to pass a parameter to the output subprogram. Clearly specify which of MS-DOS's input-output subprograms is to be used. The subprogram to display a character is subprogram number 2H. This number is stored in the AH register. The user requests MS-DOS to carry out the input-output operation using the INT instruction. This means that user interrupts the program and transfers control to the MS-DOS subprogram that user has specified using the AH register. Write a code fragment to display the character A on the screen. Mauve DL, A, semicolon, DL equals A. Mauve AH, 2H, semicolon, character output subprogram, INT21H. Call MS-DOS output character. This simple task is quite complicated to be programmed in assembly language. The task here is to read a single character from the keyboard. There are also 3 elements involved in preparing character input. As for character output, user specifies which of MS-DOS's input-output subprograms he wishes to use. That is, the character input from the keyboard subprogram. This is MS-DOS's subprogram number 1H. This number must be stored in the AH register. User calls MS-DOS to carry out the input-output operation using the INT instruction. As for character output, the MS-DOS subprogram uses the AL register to store the character it reads from the keyboard. Example: write a code fragment to read a character from the keyboard. Mauve AH, 1H, keyboard input subprogram, INT21H, character input, character is stored in AL. Reading and displaying a character. The following example combines the 2 previous ones by reading a character from the keyboard and displaying it. Example: Mauve AH, 1H, keyboard input subprogram, INT21H, read character into AL. Mauve DL, AL, copy character to DL. Mauve AH, 2H, character output subprogram, INT21H, display character in DL. A complete program. To write a complete 8086 program, use an editor to enter the program into a file. The process of using the editor, editing, is a basic form of word processing. Use Microsoft's MASM and Link programs for assembling and linking 8086 assembly language programs. MASM program files should have names with the extension 3 characters after period ASM. Having entered and saved the program as prog1 using an editor, a user must then use the MASM and Link commands to translate it to machine code so that it may be executed as follows: C greater than MASM prog1. If the program has syntax errors, he will get error messages at this point. Edit the program, correct them, and repeat the above command. Otherwise, proceed to the Link command, pressing return in response to prompts for file names for MASM or Link. H: greater than Link prog1. To execute the program, simply enter the program name and press the return key. Time-saving tip. Since the programs will start and finish using the same format, a user can save time entering this code for each program. Create a template program called, for example, template.asm, which contains the standard code to start and finish the assembly language programs. When the user wishes to write new programs, he copies this template program into a new file, say for example prog2.asm, as follows. Example: using the MS-DOS copy command, H: greater than copy template.asm prog2.asm. Then edit prog2.asm and enter the code in the appropriate place. Write an ALP to find factorial of number for 8086. Mauve AX, 05H. Mauve CX, AX. Back: DEC CX MUL CX. Loop back. Results stored in AX. To store the results at D000H, Mauve D000, AX HLT. The 8 data bytes are stored from memory location E000H to E007H. Write 8086 ALP to transfer the block of data to a new location B001H to B008H. Mauve BL, 08H. Mauve CX, E000H. Mauve EX, B001H. Loop : Mauve DL, CX. Mauve EX, DL. Dec BL. JNZ loop. HLT. Write a program to display string computer science engineering for 8086. Title: Display the string. .seg. Written by user. .model small. .stack 100H. .data. String 1 DB computer science engineering, $. .code. Main proc. Mauve AX, at data. Mauve DS, AX. Mauve AH, 09H. Mauve DX, offset string 1. INT 21H. Mauve AH, 4CH. INT 21H. Main end P. End main. Write an ALP to generate square wave with period of 200 milliseconds and address of output device is 55H for 8086 microprocessor. Start: Mauve AX, 01H. Out 30H, AX. To generate loop for 200 milliseconds using system frequency 5 MHz. Mauve BX, count 70. Label: Dec BX, 40. JNZ label, 10T divided by 7T. Mauve AX, 00H. Out 30H, AX. Mauve BX, count. Label 1, DEC BX. JNZ label 1. JMP start. Conclusion. In this chapter, we have covered the following aspects of assembly language programming. Machine and assembly language. Turbo assembler, Tasm. Assembly language of Intel 8086. Simple examples based on arithmetic and character operation,